Yeah, as we have quite a lot to get through today. Our first speaker is going to be Robbie Brady, and he is from the Offshore Renewables Catapult, I believe. And you can probably tell us just a little bit about what that is as well for any of our viewers that aren't familiar with what the ORE Catapult is as well. Brilliant. So over to you, Robbie.
Thanks, Steve. Yeah, hi, my name's Robbie Brady. As Steve said, I am program manager for the Tiger project, which is Tiger stands for Tidal Stream Industry Energizer Project, and it's a tidal stream focused project led by the Offshore Renewable Energy Catapult. The Offshore Renewable Energy Catapult lead partner in the project. We are primarily an offshore renewables technology research centre. Heavily involved in offshore wind, but also smaller technologies such as wave and tidal, with the goal really of accelerating the deployment of marine energy in the UK. So just in terms of an agenda, I'm going to give you a quick run through of what Tiger is and what it's all about. We're going to quickly look at what's tidal stream energy. Conscious some people may already have an understanding of it, I want to distinguish it from other kind of similar technologies. What are we looking to do through Tiger, and what is the Tiger challenge? Who's involved? It's quite a large partnership, so I was going to give a quick rundown of who the partners are, and quick look at the sites that we'll be working on as part of Tiger. And then, as I'm conscious, there'll be potentially some members of the supply chain here, or potential members of the supply chain. I wanted to run through what we're doing to get engaged with the supply chain. So, as I said before, Tiger stands for Tidal Stream Industry Energizer Project. It's a 45 million euro ERDF funded project. It commenced on the 2nd of July 2019, and it will run till March 2023. So it's a 4-year project, and it brings together a consortium of 18 different partners spread across the UK and France. It's funded by the Interreg Channel Manche programme. So we're primarily looking at sites in the Channel region on the UK and France side, with the kind of overall objective of linking the two industries in the UK and France, and ultimately driving down the cost of tidal energy and accelerating deployment. So as I said before, we're primarily looking at sites in the Channel region. We're Interreg funded. You can see on screen here the map of the Interreg region. So the dark green shaded areas are the areas covered by the Interreg Channel region. That's really where they want to see the maximum benefit. That's where they want to see money being spent. And that's, the aim of Tiger is for all of those regions to feel some kind of benefit from what we're doing through the project. The slight outlier is Ramsey Sound off the west coast of Wales, which was brought in because it's a particularly attractive site, and it was something of a challenge to find enough sites ready to go on the UK side. So as I said before, the Catapult lead partner in Tiger. It's run from our office during normal times in Hale down here in Cornwall. We're at the Hale Marine Renewables Business Park, so we share a building with other companies you may have heard of, such as Wave Hub. And there's kind of CFAS in there, the MMO are in there. So it's a real hub of activity in the kind of marine sector. Obviously, given the current circumstance, we're all working from home and travel's quite restricted, but during normal times, that's where you'd find us. So I think, given present company, that I need to explain the concept of tides to you. But what I did want to do was just touch on what distinguishes tidal stream from tidal range. As you'll be aware, as you may be aware, tidal range focuses on the difference between high and low water. You've got technologies such as lagoons and barrages. Examples in the UK being Swansea Lagoon and the Severn Barrage, neither of which went ahead. But they rely on the difference between high water and low water. That's not what we're looking at through Tiger. What we're looking at through Tiger is tidal stream. So tidal stream, the analogy that I find easiest to understand is to compare it to kind of wind energy. It's a very similar concept. It relies on the flow of water as opposed to the difference between the high and low tide. And the turbines capture that flow and turn it into electric energy, much the same as an onshore wind turbine does with the wind. You tend to find, ideal tidal stream sites where flow is forced between a headland and an island, for example. Ramsey Sound's one good example of that, but that's not to say that's the only place suitable for tidal stream energy. So that's just a photo of the tidal race, I believe, actually in Ramsey Sound around the beaches there. So you can just see just how much water is flowing, you know, at peak tidal times. As part of Tiger, we wanted to incorporate as many different technologies as possible. That's what we're all about. And tidal being what it is and where the industry is, you know, they're not, we haven't kind of, there's not one single sort of tidal turbine design. There's a few different designs floating around. On the left there, you've got the idea, you can see the concept of a kind of moored floating tidal device. So examples of those would be Magallanes or Orbital being a partner in Tiger. On the right there, you've got a kind of more traditional wind turbine style tidal turbine. So fixed to the bottom either by piling or gravity anchors. And an example of that would be kind of Cymec Atlantis, who are again a partner in Tiger. And there is a third concept that we're considering, which is the kind of mid-water column tidal kites, which you may have seen, specifically Monesto, Swedish company, also a partner in Tiger. And their device sits kind of halfway between the surface or some way between the surface and the seabed, and is tethered to the seabed. And it flies in a sort of figure of eight formation, much the same as, you know, if you're flying a kite on the beach, and in doing so, it drags a turbine through the kind of through the tidal flow and generates energy that way. So I said before, Tiger is all about accelerating deployment of tidal stream in the UK and France. And one of the key barriers to deployment at the moment is just the cost, the levelized cost of energy of tidal stream when compared with, you know, certainly fixed bottom offshore wind, or, you know, the really advanced technologies such as onshore wind and solar. It's just not quite competitive yet. It hasn't benefited from the same government support in the past. So what we're trying to do through Tiger is substantiate some claims that the Catapult made in our 2018 Wave and Tidal Cost Reduction Report. As you can see in front of you here, there's the current state of the art with 10 megawatts installed as we currently do. We're looking at about £300 per megawatt hour installed. As you come down the cost curve, you know, additional deployment towards 200 megawatts deployed, you reduce costs through learning by doing, you reduce the cost of capital. By the time you're up at 200 megawatts installed, you're looking somewhere in the region of £100 to £150 per megawatt hour. Going further, moving towards 1 gigawatt installed, again, you know, accessing lower debt and lower cost debt finance, learning by doing. And the hope is that you'll be somewhere around £90 to £100 per megawatt hour installed. So these were claims made in our 2018 report, but they were based on theory. So what we really want to do is put some points under this curve and you know, really prove it in a kind of a real seas environment. So through Tiger, we're going to consent new sites. We're going to get some devices in the water, the UK and France, and we're going to analyze all that, put it together, and translate that into some kind of cost reduction figures in a format that can be put in front of policymakers to really prove the point that, you know, Tidal is ready for a subsidy and can be cost competitive. It just needs that initial kickstart that those other technologies had. So I kind of touched on it just then, but how we're going to do that. So I said before, we're going to be getting devices in the water. We're going to be looking at technology, and then we're going to be putting it all together. So Tiger is separated in 3 different work packages. Work package 1 is tidal energy site development and deployment. So that's the learning by doing stuff. So getting devices in the water, consenting new sites, understanding really how much does it cost to get these things in the water and operate them and also recover them. Work package 2 is looking at the development of new technologies and products. So one of our deliverables through that work package is to come up with a range of 46 new products, systems and test specifications. And what we want to do is, you know, see how we can drive down costs by increasing commonality of components. So at the moment, developers are largely working in silos. They may well have similar problems, but they're not collaborating. They may well need similar components. but they just don't know it yet. So the idea is to get them collaborating, identify areas of commonality, and hopefully allow them to access kind of economies of scale, place larger orders, and obviously drive down costs that way. And then work package 3 is cost reduction analysis. So that's where we're putting together all the data in work packages 1 and 2, and our in-house techno-economic analysts will pull that together and put that into kind of some reports and some nice graphs that can be put in front of politicians and policymakers and say, look, Tidal is ready. We're ready to go. We've got all these sites ready. The costs are competitive. We just need your initial support in favor of Tidal Stream. Excuse me. So as I said before, Tiger brings together a considerable partnership of 18 different partners. We've got a fairly even UK and France split. I won't list them all, but we've got in there, you've got kind of device developers, you've got research bodies, so universities in both on the UK and France side, and then you've got regional agencies who are primarily there to kind of get the assist with the consenting, but also get the Tiger message out there and make sure that the benefit is felt by the various regions that are involved. So now I was just going to give you a quick run through of the various sites that we're working on through Tiger and the technology that's going to be deployed in each one. So starting off in Morbihan, down further south there, in the Morbihan Gulf, Sabella, or the actual partner in Tiger is MHE56, who's a JV that Sabella are a part of. They're going to be deploying 2 of their 250 kilowatt turbines in the Morbihan Gulf. They're actually in the consenting stage at the moment, so they're seeking consent for the 2 turbines, and then the hope is that they'll get 2 turbines in the water pre-2023, so that we can kind of do some analysis on how they're deployed, how they're operated, and also the learning from the consenting process will be invaluable as well. Then just slightly further north, on the north coast there, we've got Pampol Brehat. So there's 2 things going on there. At the moment, HydroQuest have their vertical access Ocean Quest device. So 1 megawatt turbine. That's already deployed at Pampol Brehat and was deployed pre-Tiger last summer. Through Tiger, we'll be supporting HydroQuest in continuing an extended testing campaign on that device. We'll be doing kind of a certified power curve assessment on the device, and then also decommissioning the device. So all of that is really valuable learning and will help HydroQuest understand how, where their cost of energy is at and how they can bring it down. Then once HydroQuest are out, Minesto, as I kind of alluded to before, are going to install one of their 100 kilowatt tidal kites, again at Pampol Brehat. At the moment, Pampol Brehat is the site setup is such that only certain devices can go in there. So another activity we'll be doing through Tiger is making it universal so that it becomes a test site where just about anyone can go and test a tidal device. Then furthest north, Ramsey Sound, many of you may be familiar with. Back in 2014, Tidal Energy Limited, or TEL, deployed their Delta Stream device. Unfortunately, there was a malfunction with the device and it soon went out of operation. Subsequently, Tidal Energy Limited went into administration. So unfortunately, since then, the device is sat on the seabed, unoperational, despite it being a fantastic site, grid connected with ROC accreditation, ready to go. So the partner in Tiger is Cambrian Offshore. They're going to look to recover Delta Stream and do some forensic analysis on it, because it's quite a unique case. I don't think anywhere in the world there's been a device deployed for 4 years, albeit non-operational. But it'll be good to see what kind of condition it's in, and they're potentially looking to refurbish it and redeploy. But if it's not usable, then they will be procuring new turbines, potentially a new base, and reinstalling and recommissioning. So the idea there is just get to redevelop Ramsey Sound and have it as a commercial tidal site on the UK side. And then PTEC, off the southern tip of the Isle of Wight. So PTEC's been going around for quite a long time. It's unfortunately, due to the lack of revenue support from the government, it's been put into hibernation some time ago. Just the other day, we announced that EMEC have kind of joined in partnership with PTEC to bring it out of hibernation. So they'll be looking to get that side to financial close. And then some of our device developers are going to look to design new devices to deploy at PTEC, one of them being QED with their Subhub Foundation, as you can see on screen there. And then finally down south in the Ras Blanchard, an area many of you may be familiar with due to its excellent tidal resource. I believe it has maybe it's certainly the largest tidal resource in Europe. So Cymec Atlantis and AED Normandy have formed a JV known as Normandy Hydroliens, and they are looking to consent a new site in the Ras Blanchard. And the unique part of that project, they're actually looking to use the power to sell to the island of Alderney via a private PPA. Many of you will be familiar with Alderney. Being a small island community, they rely heavily on diesel, and they're looking to do away with that reliance on diesel. And you know, with this enormous tidal resource in their backyard, it makes perfect sense that they should look to tidal. Actually, Danny, who is going to follow on from me, is going to talk a lot more about the Alderney race. And then the second partner that's looking at the Alderney race is HydroQuest. So HydroQuest are going to look to secure consent and develop a 10 megawatt commercial array, also in the Alderney race. They're two slightly different sites, not far from each other, but they do share some kind of aspects that, you know, their consent requires them to share a cable landing. Much of the onshore cable route has to be shared. So it's really encouraging to see that HydroQuest and Cymec Atlantis are actually starting to work in collaboration. Despite being competitors, they've kind of realized that, you know, the best way to do this is to collaborate for the greater good. And that's really encouraging to see, because it's something that's new for the sector. And finally, the other thing worth a mention is in work package 2, I kind of said that, you know, we're looking to come up with these 46 new kind of specifications for components, products, test specifications. A large portion of that is going to be done by Orbital Marine Power. So at the moment, they're undertaking this levelized cost of energy analysis of their tidal device. Many of you are familiar with their SR2000 device, which is now being decommissioned, and the O2 device, which is in manufacture at the moment. They're kind of identifying priority areas for cost reduction, to form a basis of design for future devices. So I expect much of those 46 kind of new products will come out in the wash through Orbital's work. And the other side, so, you know, I kind of mentioned that we've got kind of 3 work packages. The first work package is really consenting and deployment. Work package 2 is coming up with new specifications and products, and that can only be done, you know, with the full support and engagement with the supply chain. So a huge part of Tiger is trying to develop a supply chain both on the UK and French side, and also try to get them joined up. So we're doing a range of supply chain engagement activities. The first was the series of 6 supply chain events that we've just finished running, and they kind of looked at various challenges in the tidal sector. So from things like superstructure design to marine operations. And what the partners did was each partner was responsible for a different seminar. They kind of talked through almost a lessons learned. You know, they gave a lessons learned presentation from their last, you know, projects. And the idea was to get the supply chain engaged and thinking about how, you know, next time, how we can do this better. And we're already seeing, you know, quite a lot of engagement between the supply chain and those partners. So it was certainly worthwhile. So yeah, as I said, those first 6 supply chain engagement seminars have been and gone now. What we're looking to do is develop a series of further 6 supply chain events, likely to be held summer of next year and summer of 2022. And these events will kind of provide a unique insight into the Tiger industry leading projects, and hopefully identify opportunities for the supply chain to get involved in tidal. You know, there's many supply chains sitting on the companies that are kind of sitting on the periphery and just looking for that into tidal, and we're confident that, you know, Tiger can provide that. And just a final point to say, you know, Tiger is all about collaboration, knowledge sharing. So, you know, if you feel like there's anything we can do for you, or there's anything you can do for us, we're all ears. Please do get in touch. That's, you know, a big part of, you know, the conditions of the funding from Interreg. We should link up with as many other projects as we possibly can to ensure the reach of Tiger is maximised, and as many people feel the benefit of that funding as possible. So please do get in touch if you feel there's anything we could work on together. I'm going to stick my contact details up on the next slide. Yeah, so there's my contact details. I've been Robbie Brady, Tiger Program Manager. My email address and mobile number just on the screen there. So please do get in touch. But otherwise, I'm going to hand over to my colleague, Danny Coles of Plymouth University. Thank you.
Okay, thanks very much, Robbie. So Danny will be up next. Robbie, you'll see there's a couple of questions have appeared in the chat. So maybe you could answer those through the chat box while Danny starts giving his talk. Okay.
Thank you. Okay,
over to you, Danny.
Thanks, Steve. Thanks for having me along today. And thanks, Robbie. That was a good introduction. Hi, everyone. Good afternoon. As Steve said, I'm a research fellow at Plymouth University working on the Tiger project. And today I'll be giving a presentation looking at the energy yield estimates and aspects of array optimization and also cost of energy and how that all feeds into the Tiger project. So just to give a bit of background to start with, these maps here are highlighting some of the main regions of the UK where there is a tidal stream resource. There's a UK-wide study that was commissioned by the Carbon Trust that concluded that the UK practical resource for tidal stream energy is around 34 terawatt hours, which is equivalent to around 11% of the UK's electricity consumption over a year. And so we have a reasonable level of confidence that there's a significant resource out there that we can harness. And these maps are really trying to highlight that, really. I won't be able to go into too much detail on an individual site level, but you know, there are Crown Estate lease plots that have been allocated, especially in the Orkney Waters and Pentland Firth region of Scotland, on the west coast of Scotland and the UK as well. Also got Wales, Anglesey and Ramsey Sound. And then also the Channel Islands, which obviously fits into the Tiger domain of research. And so, whilst we're confident that there is a resource there, there is still a reasonable amount of uncertainty as to how much could be practically harnessed. And that is often to do with the fact that environmental sensitivities are fairly unknown when looking at large-scale deployment of devices. We also need to get a better handle of what the cost of energy is to understand what's practically possible to carry out. So this work really focuses, rather than on the sort of individual single device scale that Robbie has presented, this takes a bit of a different angle in that it's looking at the larger scale deployment of tidal stream energy to really understand what is the size of the prize, if you like, for tidal stream energy, and how can we, you know, reduce that uncertainty in what the practical resource is in order to really drive policy and drive support for this industry. So just a couple of plots here, just to give a bit of context as well. The plot on the left is showing the relationship between time and the cumulative capacity in Europe of tidal stream energy. And you can see that between 2010 and 2019, there's been a significant increase in the capacity that's been installed. Some of that capacity is still operational, such as the Maygen array up in Scotland and other sites, and some of it's now been decommissioned, having completed testing. The plot on the right is similarly showing a relationship between time and the cumulative energy production, and we're now at a stage where we've nearly reached 50 gigawatt hours. That energy production is predominantly from the Maygen array in Scotland, and as well as the orbital device that was installed at EMEC, and they are planning to install a new device at EMEC very soon, and also the CGen device that was installed at Strangford Lough and has now been decommissioned. So, you know, this is obviously showing that there's been good progress made, and a lot of that progress has been supported through the ROC subsidy support, which is now no longer available for, it's now been changed into the CFD allocation. And we're looking at now trying to provide evidence for further support for tidal energy in order to further develop the industry. So my presentation will focus on the Alderney Race, or Ras Blanchard as it's also known. This map here is just showing an idea of the level of energy or spatial variation in energy, if you like, around the Channel Islands region. The Alderney Race has been identified as the main kind of site for tidal stream energy development. Although there are others. There's the Casquettes on the west side of Alderney, Northwest Guernsey, Sark, and also Northeast Jersey as well. So, you know, there are multiple locations, but most time and effort has been spent at Alderney Race, and will be done so within the Tiger project. So historically, what I'm going to do with this presentation is kind of give a run through chronologically of how energy yield estimates have developed through time at Alderney Race. This plot here is showing a layout that was considered back in 2004 by the research group at Southampton University. And this layout is really based upon fairly limited data, which was basically the only thing that was available at the time. So it's not a criticism of the research at all, but so it was really relying on, you know, Admiralty chart data for flow speeds and relatively coarse resolution bathymetry data to try and understand where to locate turbines, but also how big those turbines should be in terms of swept area and rated power as well. And this study estimated that the annual energy yield from this array, which is a 3.26 gigawatt array, so very, very large array, obviously, is 7.24 terawatt hours, and that's equivalent to a mean power of about 0.8 gigawatts, or if you like, 2.4% of UK electricity consumption on an annual basis. And the research that I've carried out is really trying to understand what is the accuracy of this estimate, given the sort of drawbacks in terms of resolution of flow data and bathymetry data. And also it's important to state that this study doesn't consider the blockage effect of the array, where adding turbines within Alderney Race is going to block the race up and potentially divert flow around Alderney Race and into that casquettes area that I showed on a previous map. So this is an example of the work that's been carried out since. So the plot on the top left is showing the same array layout that I showed on the previous slide. The contours on that plot on the top left are depth, so bathymetry. So what we've done is we've actually modeled the tidal resource within Alderney Race using a program called Telemac 2D. And some of the outputs from that model are shown on the top right panel. And this plot is really showing, the color scheme is really showing in what regions of the race are the flow speeds increasing versus the ambient flow when you don't have turbines within the resource, and in which regions are they reducing. So you can see the green and blue regions where the turbines are located. You see this significant reduction in flow speeds, and then you also see a significant increase in flow speeds in between the two arrays and also on the flanks of the arrays either side of the race. And so what this is really highlighting is that blockage is obviously a very important thing to consider when carrying out energy yield estimates, because the flow speeds are reduced significantly at the locations of the turbines. And for that reason, you really need to run these sorts of simulations in order to estimate energy yield with any confidence. The plots below are basically just showing a time averaged representation of how the flow speed changes versus the ambient flow over a spring neap tide. And again, it's a flood and an ebb, peak flood and peak ebb tide. And so it's again showing that significant increase and reduction in flow speeds that you see across the race. So why is that important? Well, power that's produced by a tidal turbine is proportional to the flow speed cubed, and it's also proportional to the swept area. And so, you know, if you're getting these big reductions in flow speed at the locations of the turbines, then your power is going to reduce significantly. The swept area is also important. As I mentioned in that 2004 study, the swept area of the rotors was selected based on fairly limited bathymetry data. And so I'll show in a future slide that actually in a lot of cases, an inappropriate swept area was chosen. And so we could potentially maximize power by having better bathymetry data to understand what the spatial resolution in depth is. So the plot on the left, bottom left, is just showing a typical power curve for a turbine. So you've got flow speed on the x-axis and power on the y-axis. And it has this cubic relationship between flow speed and power, as I mentioned. So you see a quick increase in power as the flow speed increases above the cut-in speed of the turbine. And then eventually you'll reach the rated speed of the turbine, where basically you're generating your rated power. So typically for a device at the moment, full scale device could be sort of 1.5 megawatt or 2 megawatts maybe in scale. And so by increasing the rated power, you're increasing the maximum power the turbine can produce. On the right hand side, it's just showing a similar thing, where if you increase the rotor diameter, then you're increasing the power that you can generate at below rated speed. And so both approaches are suitable in terms of maximizing power per turbine. And I'll go into that in more detail in a future slide. So what we did with the updated study is we looked to add detail to the model incrementally and see how that affected the energy yield, or estimated energy yield, should I say, of the array. So case one in this slide is the study done back in 2004. So as mentioned, it had a relatively coarse flow resolution and bathymetry resolution. It didn't consider array blockage. It used a power coefficient of 0.3 to estimate power. And what we did in case two is we improved that using the flow simulation that I showed. And so we increased the flow resolution to around 250 meters. So that was the only change we made to start with. And we saw that the energy yield reduced from 7.4 terawatt hours to 6 terawatt hours. In case three, we added further detail by including the array blockage that I alluded to with the flow simulations. And that, as you'd expect, shows a significant reduction in estimated energy yield from 6 terawatt hours to 2.3 terawatt hours. Case four, we actually updated the power coefficient because we now have better understanding of how the turbines are performing at real sites, such as Maygen, who have issued a lessons learned report that has this updated figure of power coefficient of 0.41. So that increases the energy yield from case three to 3.2 terawatt hours. And then finally, we actually looked at reducing the array capacity, because what was happening was that there was so much blockage that the turbines weren't even reaching their rated speed. And so we could maintain the same level of energy yield of 3.2 terawatt hours, but using a much smaller or less engineered, if you like, array of turbines. So I think this work is important in highlighting those deficiencies in historic energy yield estimates, but also in highlighting and pulling out methods for optimizing and improving array performance moving forward as well. And there's no reason why we couldn't improve on that 3.2 terawatt hour figure in case seven. And I'll move on to that now. So, as I said, this work has identified further array improvements. So the plot on the left here is showing the time averaged flow speed across the Alderney race. And as you can see, the yellow regions are the regions of highest flow. And as you can see, the turbines, in some cases, are not located in those highest energy regions. And that's as a result, as I mentioned, of only having low resolution flow data initially back in 2004 when this array was designed. Another aspect, as I've already alluded to, is the rotor diameter. And so the plot on the right is showing for each sub-array within this array, which is shown for each point on the left-hand side, the rotor diameter can be increased. So the blue bars are showing the maximum rotor diameter that would be allowable at each location. And the orange lines are showing the rotor diameter that was actually used in the study. So in most cases, okay, there are some exceptions where actually rotor diameter actually have to reduce, but in most cases, the rotor diameter could increase and significantly. And we've calculated that would lead to an increase in total swept area of the array of about 30%. And so you'd expect to see similar, well, maybe similar sort of levels, at least in magnitude of energy yield uprise as a result of that, assuming blockage doesn't impact on things too much. So, okay, so that's sort of as far as we can go with a kind of that sort of approach to array design. But what we're doing now is we're taking that further by looking at array optimization. And what I mean by that really is a method where we can link the hydrodynamics and how the hydrodynamics change as a result of putting turbines in the water to the optimal array design. And that's really the motivation for this new work that we're carrying out now. And what we're looking at doing is implementing gradient-based optimization within site-specific hydrodynamic models. And this has been developed through software packages such as Tidal Farm and Thetis, both developed at Imperial College London. And the sort of summary of this approach really is that you start with an initial kind of idea of what the array might look like in terms of number of turbines or spatial variation. And then you go through an iterative process. So you basically carry out a simulation that carries out the shallow water equations to look at what impacts the turbine has on the flow field and what power could be generated from that array. And then look at an optimization where you carry out the adjoint equations in order to estimate a profit gradient. And what this ultimately does is look at ways of improving the array performance through changes to the array design. And that is what we're looking at the moment is focused mainly on the location of turbines within a site. But there are other aspects that you could optimize for as well, and I'll go into that in a future slide. But once you've carried out that step, you can recalculate the energy yield of the array and the impacts that array has on the flow dynamics and the blockage, and then carry out that iterative process until you come across a converged optimal solution. So I can demonstrate this in this video. On the top here, we've got a regular array of turbines. And the flow is going to come from left to right, although the flow field won't actually be shown. On the bottom here, we've got a plot that shows the relationship between the iteration within the optimization and the power production. And if I just play this through, what you'll see is that as the array is optimized and as the turbines move within the optimization, we see a significant increase in power production. We're going from 300 megawatts as a mean power up to 400 megawatts, so 30% increase in power production as a result of optimizing the array. So this is obviously very important in that we're better harnessing the available resource. It will lead to significant cost reduction, as I'll go into in a future slide. And you know, this obviously fits in and ties in well with the aims of the Tiger project. So yeah, so this slide is really just to highlight that, you know, we can carry out this sort of approach on any type of array, any size of array, and each site will be different, and so we need to consider the site-specific characteristics in terms of bathymetry and flow speeds and those sorts of things. But we are seeing quite significant increase in mean power as a result of array optimization. Here again, we're seeing a mean power increase of from 55 to 75 megawatts. So we've taken this work and we've implemented it within the Alderney race. And this plot here is showing the array layout, where yellow is showing a high density of turbines and blue is showing no density of turbines. And as we move from figure A to B to C and then eventually to F, we've set up the optimization to implement what we call a break-even power. So that effectively is the power that the array must generate. The mean power that the array must generate. So as we go from A to F, we see that the break-even power, PBE, has reduced from 500 kilowatts to 0 kilowatts. And so as a result of that, as we move across from A to F, it's more acceptable to add turbines to the array and for them to generate less mean power. And this is kind of synonymous with cost as well, and I'll go into that in the next slide. So what we see is that as the break-even power reduces from A to F, we see initially that turbines are installed on the French side of Alderney race in 2 rows. And then as we reduce break-even power, we see that the rows sort of expand out towards Alderney and span the race. So it's interesting to compare this optimal design to the one previously considered back in 2004, where now we see that the turbines are spanning the whole race in order to try and minimize those blockage effects that we saw, where flow was accelerating between the arrays and around the arrays. Case F, it's important to note, case F is not really a realistic scenario, in that you never see that number of turbines within the race. Obviously, from a cost perspective, it would be far too expensive, and also from an environmental point of view. And so I'll move on to that now. So what we've actually done here is those arrays I've shown you effectively are optimizing not for power, but for cost of energy, where we can try and minimize our cost of energy within the optimization. To do this, we've used input figures from literature that are publicly available, and the table on the top of the slide here is showing a summary of those figures. One of the challenges we're finding at the moment is that in the literature, there's quite a big range of figures. So for example, for CapEx figures, these are fixed CapEx figures. We're finding figures between sort of 14.4 and 5.6 million per year. And unsurprisingly, that results in quite a big range of, or high level of uncertainty in terms of the LCOE that we think we could achieve. Nevertheless, we looked at ways of minimizing that uncertainty. So the plot on the bottom left is showing the relationship between the number of turbines added to the array and the net average power of the array. That's the blue line. So as you increase the number of turbines, you increase the average power, but there's a diminishing return because of the blockage effect, where adding more turbines reduces the number of power generated per turbine. And that's the relationship shown by the red line on that plot. The bottom right plot is showing the relationship between number of turbines and LCOE. And as mentioned, we're seeing that depending on which CapEx and OpEx figures we're inputting into the model, we're seeing a high range of LCOE figures coming out of this model. As a way of trying to minimize that LCOE uncertainty, what we looked at doing is running a Monte Carlo simulation, where instead of considering cases where all costs were either at the high or low end, it would be better to normally distribute those costs in order to understand what the P10 and P90 and P50 LCOE would be. And as you can see on the plot, that does reduce the uncertainty quite significantly. The pessimistic and optimistic kind of outliers, if you like, in terms of the sort of extreme cases are the blue and the green lines, whereas the P10, P90 and P50 are the ones in between that. However, we do acknowledge still quite a range of LCOE that we're seeing from this P10 to P90 range. And so we're looking now at ways of minimizing that uncertainty through better definition of the CapEx and OpEx figures that we're putting into this model. So just to conclude then, as I've shown in this presentation, we're seeing a very steep cost reduction in the early stages of array development. I should have pointed that out. Sorry, let me just go back to that slide. Here we go. Yeah, so the bottom right plot, we're seeing the trend is typically a very steep reduction in LCOE to start with, and that's as a result of both the array optimization itself, but also the economies of volume that you see, because fixed costs are able to be shared over a larger number of turbines, but that only goes so far. It's also worth noting from the inflection point on these lines that that's ultimately the effect of blockage, where, okay, you're getting these economies of volume to start with, which is great, and you get them going through as you increase the number of turbines. You also get the competing aspect of array blockage, which reduces your energy yield per turbine. And so they're kind of competing, and that's the reason for the shape of that plot. The results show that for an 80 megawatt array in the East Race of Alderney Race, we're looking at, based on typical CapEx and OpEx figures, an LCOE of around about 110 megawatt hours. Again, these are figures based on CapEx and OpEx figures published in literature, and we're now looking at trying to validate those numbers. And so there's a bit still to do there. And finally, the Monte Carlo analysis that we've done is significantly reducing that level of uncertainty in LCOE. However, again, there's still work to be done there to further reduce that uncertainty within acceptable bounds. The further work that we're now looking at doing is looking, as I said, to reduce that level of uncertainty. We are looking to optimize turbine design, not only to consider LCOE, but also looking at multi-objective optimization to also minimize environmental impact, which, as I mentioned at the top of this talk, is another big uncertainty that is driving that uncertainty in the practical yield that we can achieve. And we also want to improve the spatial resolution within the ordinary race in terms of the modeling work as well. And we also want to apply this work to the other locations within the Tiger project. So the animation here is showing a Thetis model of the Ramsey Sound that we've now validated with field data. And we're looking at now implementing these sort of optimization routines to look at how best to utilize that resource as well. So I think that's my time. I think I've covered everything I need to. And yeah, thanks for listening, and welcome any questions.
Brilliant. Thanks very much, Danny. And well done to you and Robbie for getting through a terrific amount of slides in the time